In our previous lecture, we introduced the discrete time autonomous system, which the notation for which notation we use is this: x plus equals f of x, or nth order system. F is a mapping from Rn to Rn, and Rn is the space where our state resides in. Okay, so this shorthand notation just means this. Okay, in the if you write it in the long form, which means that the value of the state, okay, at the next time instant, and by time instant we mean discrete time k, starting from the initial time 0, and then it goes 1, 2, 3, and so on. Okay, the positive integers. So if you know the value of the state or the solution at some discrete time k, then the value of the solution at the next time, okay, k plus 1, is simply you take the value at time k, you pass through the mapping f, and the mapping f gives you value at the next time instantly. So in a sense, this mapping f is your one-step solution to the future. Now for this autonomous system, the definition of equilibrium, qualitatively speaking, was same as the definition of equilibrium for a continuous time system, namely a point in Rn is an equilibrium point for the system if you start at that equilibrium point. If you start at that point, you remain at that point for all future times. Okay, and that description immediately suggests that an equilibrium point should satisfy the following equation. Okay, f of xe equals xe. If you have a state, if you have a vector that satisfies this equation, okay, and then that vector in Rn, or that point in Rn, is an equilibrium point of the system. So once the equilibrium point is defined, or in such a way, we introduce the definitions of stability for the equilibrium point, and those definitions, again, qualitatively speaking, were same as those in continuous time. Okay, namely, the equilibrium point, and without loss of generality, we took our equilibrium point to be the origin. Okay, so the origin is said to be stable. If you start close to the origin, you remain close to the origin for all future times. Okay, if it's unstable, if it's not stable, and if furthermore a stable equilibrium point satisfies a property that if you start sufficiently close to the origin, all the solution converges to the origin, then you have asymptotic stability. If all solutions converge to the origin, you have asymptotic stability, okay, for a stable equilibrium point. And finally, if the convergence is exponential, then you have exponential stability of the origin. Now, having defined the stability concepts for the discrete time autonomous system, the next natural question that we ask is how to establish stability or asymptotic stability of a equilibrium point for a given discrete time autonomous system. Okay. For continuous time case, the most powerful tool we had was the Openness theorem, plus sometimes the Lassalle's invariance principle. It turns out that those two important tools have very nice and natural extensions to the discrete time case, and those we will study soon enough. But before we introduce those results, those tools, the Openness theorem and invariance principle, let's make sure that we remember the fundamental results for stability for the LTI case. Okay, so we're gonna now remember the linear theorems, and then we're gonna move on to general nonlinear case. Okay, first theorem is about stability. Then we will talk about asymptotic stability for the LTI case. The origin of the discrete time LTI system autonomous, okay, x plus equals ax, where A in this case is an n by n matrix. It turns out that stability is directly related to the eigenvalue positions of the system matrix A is stable if and only if, so it's an equivalence result, as usually is the case for linear systems. All the eigenvalues let's call them lambda I of the system matrix A satisfy for continuous time x equals ax. The condition was such that all eigenvalues are on the left half plane, and for the eigenvalues that are on the imaginary axis, the corresponding Jordan block had to be of size 1 by 1. Okay, and that condition translates into discrete time in the following way: all the eigenvalues have to be on the unit disk. Okay, in other words, the magnitudes has to be no larger than unity, and if you have an eigenvalue on the unit circle, that is, whenever lambda I magnitude equals 1, the corresponding Jordan block has to be of size 1 by 1. Is of size 1 or 1 by 1. Okay, so that's the necessary and sufficient condition for stability of an LTI system. Now, as for asymptotic stability, we have the following result: for x plus equals ax, the following four conditions are equivalent. One, the origin is asymptotically stable. Two, all the eigenvalues are with magnitudes that are strictly less than 1. Of A, where for the continuous time this condition is replaced by all the eigenvalues are with strictly negative real parts. Okay. Here we have the Lyapunov interpretation of stability for linear systems for each symmetric positive definite matrix of size n by n being the order of the system. There exists another symmetric positive definite matrix P that uniquely satisfies the so-called Lyapunov's equation for discrete time linear systems: ATPA minus P plus Q equals 0. And for the origin is globally exponentially stable. So for a linear system, asymptotic stability and global exponential stability, they are the same thing. Okay. We're not going to prove the entire theorem. We're going to prove the part that is important for the Lyapunov theorem that we will introduce later on for the nonlinear case. Okay. So what we're going to establish now is that 3 and 4, those two conditions, are equivalent to one another. Okay. So let's prove the equals between third and fourth conditions. Okay. So let's begin by this direction. Okay. 4 implies 3. Now, the origin being globally exponentially stable means that, according to our definition of global exponential stability from the previous lecture, all solutions satisfy that their norms are upper bounded by C representing the overshoot, gamma representing the decay to the K, times the norm of the initial condition x0, okay, with C positive and gamma is again a constant somewhere between 0 and 1. Okay. Now, suppose that we're given some Q matrix that's symmetric and positive. And with that Q, what we're going to do is we're going to define P, or we're going to construct P as an infinite through an infinite sum. But for that, we're going to consider a finite sum. Okay. Therefore, given Q, define P sub n as this matrix. K equals 0 to n. So n is an integer, okay, positive integer. A K T Q A K. Okay. So A K T simply means A transpose raised to the power K, or A to the K transpose. They're both the same thing. Okay. And also, by definition, the 0th power of any square matrix is identity. Okay. So therefore, what we're talking about here is, okay, for K equals 0, this is identity, so we're left with Q. Then for K equals 1, we have A transpose QA. For K equals 2, we have A square transpose QA squared. And up to, we stop at K equals N. Okay. Now, we're going to prove that as n goes to infinity, this term converges to something, and that something that it converges to will be our P eventually. Okay. So to prove that, we first prove the following statement, the following claim: P n, okay, is a Cauchy sequence. By which we mean, remember Cauchy sequence definition from perhaps 541. That is, for each positive number, no matter how small, you can always find an index such that for all indices larger than, all pair of indices larger than that index, you take the difference of the two members corresponding to that pair of indices. You take, okay, that the norm of that difference is never larger than epsilon. Okay, so that's the definition of Cauchy sequence. Okay, for each epsilon, we can find an index k such that for all indices n and m larger than that fixed index k, which depends on the epsilon that we start with, we have Pn minus Pn norm less than epsilon. Okay. Now this claim requires a demonstration, so let's do that. This claim is true because, okay, since we can write the solution explicitly as xk equals, okay, so what's the system? System is x plus equals ax. Start from initial condition x0. So what's x1? x1 is a times x0. Okay. What's x2? x2 is a times x1. x1 was a times x0. So x2 is a times x0. So that's a square x0. And so on. So that means x of k, the value of the state, value of the solution at the kth time instant, k's are discrete time, equals simply a raised to the power k, and then that multiplies the initial state, x0. We can write for any initial state other than 0, a k x0 norm divided by x0 equals xk over x0. Okay, basically, we use this equality. If this is equal, clearly the norms must be equal, and then those norms we divide by the norm of the initial condition, x0, which is different than 0, so everything is fine. Now, the reason that we did that division is because this ratio, xk over x0, is upper bounded by that c times gamma to the k. Therefore, this is less than equal to c times gamma to the k. So let's mark that discovery by star. Now we can forget about this middle term. What we have is norm of ak x0 divided by x0 is always upper bounded by c times gamma k. Okay? Since this is true for any x0, we can maximize this, and that maximum value throughout all x0s other than 0 must still be upper bound by c to the gamma k. And the maximum value that this achieves is no other than the induced Euclidean norm of this matrix a to the k. Therefore, thanks to this decay relation, we have obtained an upper bound on the induced 2 norm of the kth power of the system matrix. And that will be very useful in our demonstration. How do we proceed from there? Note that x0 can be chosen arbitrarily. Okay. Hence, as we said, inequality star gives us an upper bound on the norm of a to the k. A to the k is never larger than c times gamma k. Okay? So even though c is something large, a large number, eventually, as k goes to infinity, this will dominate, and this becomes closer and closer to 0. So as k goes to 0, this norm, kth power of a's norm, is converging to 0. Okay. Now, to prove that this is a Cauchy sequence, let's apply the definition of Cauchy sequence. Okay, so you give me an epsilon, and then from that epsilon, now I will choose a k, an index, capital K. Now, given epsilon, choose capital K large enough. Okay. So that norm of Q, C squared gamma squared 2 to the K, 1 minus gamma squared is less than epsilon. Okay. Now this is norm of Q. Q is the matrix that we started with. Okay. So, but it's constant because once Q is fixed, it's constant, and then C is constant. Okay. And then gamma is less than 1 between 0 and 1. Therefore, gamma squared is between 0 and 1. So therefore, 1 minus gamma squared is positive. Okay. And that could be quite small, which makes everything, which might make everything large for a while. But since we can choose K, anything, what we have here is gamma squared raised to the power K. Gamma squared is between 0 and 1. Therefore, no matter how small this epsilon is, we can always find a K, capital K, large enough so that this whole thing is smaller than epsilon. Due to, once again, the fact that gamma is between 0 and 1. Okay. So, with that K satisfying this inequality, suppose now that N and M satisfy N and K. Okay, so those are N and M in the definition of a Cauchy sequence. Now we're going to show that this difference, the norm of this difference, Pn minus Pn, cannot be larger than epsilon. We can write the following. Pn minus Pn, and then we take in the norm. This equals the norm of K plus M plus 1 to N AK transpose Q AK. So N is the sum running from K equals 0 to N. N is the sum running from K equals 0 to N. Therefore, the difference clearly is the sum that runs from M plus 1 to N. Okay. And then this can be upper bounded by K equals N plus 1 to N. The product of the norms. Okay. Now this Q doesn't depend on K, so we can take it out. The norm of AK we know is upper bound by C gamma. Okay, and norm of a matrix and its transpose are the same. Okay, for the in use norm. Therefore, here we can consider this as the norm of AK appearing twice. Okay? Therefore, what we can do is we can outbound this by Q. Okay, K equals K and C gamma K squared, because AK transpose, the norm of AK transpose, same as norm of AK. Furthermore, we can always replace N with something larger, and why not replace it with the number that's as large as possible, which is infinity. Okay, and we have this inequality. And now we can write this equals Q, and we can exactly compute that, okay, which is C squared gamma 2K 1 minus gamma squared. And that, because we have chosen k large enough, is less than epsilon. Okay. That proves that Pn is a Cauchy sequence. Therefore, it has to converge somewhere. Now, since Pn n equals 1 to infinity is a Cauchy sequence, the limit exists, and we're defining that limit as P. P limit n goes to infinity, P sub n exists. Okay. Now what remains to be shown is that P satisfies the Lyapunov's equation, and it does that in a unique fashion. Okay. So by definition, P is symmetric because it's sum of symmetric matrices, and also it's positive definite. Why? Because Pn was Q plus A transpose QA plus A squared transpose QA squared, and so on. So this is positive definite, and the remaining matrices are all symmetric, positive, semi-definite. We cannot be sure whether they are symmetric, positive or positive semi-definite, depending on whether A is singular or non-singular. But nevertheless, we have a positive definite matrix as the first entry, and you add into that positive semi-definite matrices, and the sum will always be positive definite. Okay. So, by definition, therefore, this limit P is symmetric and positive definite. Now let's show it satisfies Lyapunov's equation. Now, ATP A minus P plus Q equals what? A transpose, then write P, K equals 0 to infinity, A K transpose Q A K, A minus K equals 0 to infinity, A K transpose Q A K plus Q. Okay. This is P. Here also we have P. And that we can write as, since we're multiplying A transpose from left and A with right, what happens is you're simply increasing the index by 1. So what happens is you can write K equals 1, A K transpose Q, A K, and then you increase the upper index by 1 also. Okay. Now one nice thing about infinity is infinity plus 1 is again infinity. Okay, so we have that. Also, this sum we can write as, for K equals 0, these matrices are identities, so we have Q plus, then you can start the summation from K equals 1 to infinity, A K transpose Q A K, okay, plus Q. Now this Q and that Q will cancel, this term and that term they cancel because of this minus sign here, and we have what we want. Okay, this equals 0. Therefore, the Lyapunov's equation for discrete dominant system is satisfied. How about uniqueness? Okay. Now, the statement in theorem claims that there is a unique P satisfying ATP A minus P plus Q equals 0. The equation. We're going to prove this by contradiction. Okay, so we're supposing that this P satisfying this equation is not unique. That means we can find two separate P's, we can call them P1 and P2, such that this equation is satisfied. Then there would exist two P's indices P1 and P2 different than one another. And by the way, these indices should not be confused by the index that we use here. Okay, so we're they're just the indices used for our contradiction. Okay, so that's if you want, you can put tildes, okay, on top of P's. Both satisfying ATP A minus P plus Q equals 0. Okay, so let's put I here. And no matter what index you choose, or no matter what you choose as P1 or P2, both satisfy this equation. Which implies, okay, so write this equation for I equals 1, write this equation for I equals 2, subtract one equation from the other, the Q will disappear, and what you will have is AT P1 minus P2 A minus P1 minus P2 equals 0. Okay. This yields AK transpose P1 minus P2, AK equals P1 minus P2. Okay. Going from this line to that line is quite obvious. And then, if that's true for any k, clearly it should be true for the limit where k goes to infinity. Therefore, we can write P1 minus P2 equals AK transpose P1 minus P2 AK for any k. If that's true for any k, clearly we can talk about this limit. Okay, which is also true in the limiting case. Now this equals 0. Why is that? This is fixed, the matrix in the middle, and these AKs, they converge to 0. Because the induced norm is upper bounded by C gamma k, and gamma is less than 1. Therefore, as k goes to infinity, this norm has to go to 0. Therefore, the matrix itself has to go to 0. Therefore, P1 minus P2 must be 0. But that would imply that P1 equals P2, which contradicts our initial assumption. That implies P1 minus P2. So therefore, we have proven that if the origin is globally exponentially stable, then for each symmetric positive definite Q, there exists a unique symmetric positive definite matrix P satisfying the Lyapunov equation. Okay, now we're going to prove the other direction. Okay. That is, suppose that we have a symmetric positive definite matrix that satisfies this equation. Okay, for some symmetric positive definite Q. And then from this, we will try to achieve the exponential convergence of the solution to the origin. Suppose we have P symmetric positive definite and Q symmetric positive definite, both together satisfying the Lyapunov equation. ATP A minus P plus Q equals 0. Now, we're going to show convergence of the solution by the help of a Lyapunov function. Okay, so this is this in a way tells us why the nonlinear theorem, Lyapunov's theorem, which we will present soon enough, has to work qualitatively speaking. Okay, so define this scalar function x transpose p of x. Okay, since p is symmetric positive definite, this is a positive definite function of x. It's always positive for non-zero x. Okay. In fact, we can say more about that. We can write lambda min p, because it's symmetric positive definite, all the eigenvalues are real and positive, and those eigenvalues can be used in the following: upper and lower bound for v of x. V of x, and it's upper bound by the maximum eigenvalue of matrix P times the norm square of the state x. Now, given any solution x of k of the system x plus equals ax, which we can write explicitly to equal ak times initial state x0, we can write the following. Let's take the difference, or the one-step difference of our so-called Lyapunov function. Okay, so this difference, in a sense, imitates what we have been writing as v dot in the continuous time case. Okay, so this is sort of a discrete time version of derivative, or we can call it a discrete derivative of this function v along the solutions of the system. Okay, so what v dot is for continuous time systems now becomes this difference v of xk plus 1 minus v of xk. Okay, the discrete derivative of v along the solutions of the system. Anyway, now we're not considering any system, we're considering a linear system, and this difference can be written explicitly as following: x. Okay, it equals xk plus 1 transpose p times xk plus 1 minus xk transpose p times xk. And xk plus 1, okay, equals a times xk, okay, because we're talking about a linear system. So this, therefore, can be written as a transpose p a xk. Okay, this thing is xk plus 1 minus xk transpose p xk. Okay, this is xk plus 1. And this is transpose. And that can be written as xk transpose times something times xk. What this something is a t p a, and here we have minus p. And we have the relation between A, P, and Q. Okay, so called the Lyapunov equation. Therefore, this thing equals minus Q. That equals minus xk transpose Q xk. Okay, now this expression, x transpose Q xk, also this is lower and upper bound by lambda min Q norm square of x and lambda max Q norm square of x. Okay, and using that, we can write this. This is less than or equal to minus lambda min Q x k squared. And the lambda min Q is something positive, because Q is a positive definite matrix. And then we get upper bound minus norm of x squared by, okay, using this upper and lower bounds for v, and right, lambda min q lambda max p and v of x of k. Okay. Where we upper bounded minus norm of x squared by minus v over lambda max p, which directly follows from this part of the inequality, and then you multiply both sides with minus 1, which sets the direction of the inequality, and then we have this. Now what we're going to do is, we're going to take this v of xk and throw it to the other side, and we obtain an upper bound on vxk plus 1 in terms of v of xk. Okay, so let's write them down. V of x of k plus 1, therefore less than or equal to 1 minus lambda min q over lambda max p times v of x of k. Okay. Now this is positive, this is positive, this fraction is positive, and therefore this whole thing is less than 1. And it cannot be negative because it's upper bounding something positive. Okay. So let's call this beta. Okay, and beta is strictly less than 1. Therefore, what we have obtained is v of x of k plus 1. Okay, so what we have obtained is v of x of k plus 1 is less than or equal to beta times v of xk. Okay, so that means v of, I'm going to call it just 1. V of 1 is less than or equal to beta times v of 0. V of 2 is less than or equal to beta times v of 1. V of 1 is less than or equal to beta times v of 0. Therefore, v of 2 is less than or equal to beta times v of 0. Okay, so that can be generalized into this. V of x of k is less than or equal to beta raised to the power of k times v of x of 0. Let's call this inequality double star. Now, basically, we're done. All we're going to do is we're going to use this upper and lower bounds once again, and we're going to translate this inequality into the exponential decay inequality for the solution, which will give us global exponential stability by definition then. Now, double star that we just obtained yields the following: x of k norm square less than or equal to, using the upper and lower bounds, lower bound and v, 1 over lambda min p v of x of k. Okay, and then by star, this is less than or equal to 1 over lambda min p. This is less than or equal to beta to the k v of x0 v of x0, and then we can upper bound v of x0 by the norm square of x0 times lambda max p over lambda min p beta to the k and norm of x0 squared. Okay, therefore, the norm square of the solution at the time is k is less than or equal to this whole thing multiplying the norm square of the initial state. Therefore, we can write by taking the square root of both sides, norm of x of k less than or equal to lambda max p over lambda min p, take the square root, times beta, which was 1 minus lambda min q over lambda max p. Okay. And you take the square root. Then you raise that to power k. Okay, this is simply square root of beta. Because beta was defined here. Then times norm of initial condition. Okay. And that yields global exponential stability because norm of x, k less than equal to c times gamma k, which is less than 1 times the initial norm of the state.